Okay, hello again. I hope you can stay through this. I hope I can stay through this as well. Again, I changed the topic a little bit. We've been doing some work on sports aerodynamics, and I thought I will show you something that we have been doing. There's a whole lot of students who have worked on this. Many of them actually are undergrad students. For example, Kunjal Shah was an undergrad student when he did this. Aman and Daksh, they were also 4-year students. They are pursuing their masters now. And so on. So the work is motivated by our badminton club. Okay, so there are some of us who play badminton every morning. This has been going on for almost 25, 30 years. So these are all my colleagues. You may not recognize me in this picture, but I'm there in all of them. So I can give you a hint that this is my partner, my badminton partner. Okay, we played a lot of doubles together, and I just tag along. He's really a good player. So the idea was that we usually play with a duck feather shuttlecock. So, but they are very expensive. So we shifted to the nylon shuttlecock, and the flight is not the same. So the question is, what is the difference? Is there an aerodynamic difference between the two? So those kind of things are the motivation. So what I plan is show you a little bit about bluff body flows. You already know most of the things I want to say, but just a review. Then I will show you some experiments on different projectiles and different sports. Talk a little bit about cricket ball because a World Cup is going on. Then, of course, the badminton shuttlecock and some recent work on frisbees. It's in a very nascent stage. Okay, so the science behind all this emanates from the boundary layer, laminar versus turbulent boundary layer. So here is a picture of drag coefficient with Reynolds number. So drag coefficient is the force non-dimensionalized with the dynamic pressure and the frontal area, which is just circular. And the Reynolds number is also based on the diameter. So this red color is the drag force, and blue color is the non-dimensional force, which is the drag coefficient. So up to a certain Reynolds number, the drag coefficient is virtually constant. And you can see the drag force increases as V square. And then once the boundary layer becomes turbulent, then there's a sudden reduction in the force. You can see the red color curve. So you increase the speed, but actually the body experiences less drag. And that's because the boundary layer has become turbulent. So this is a laminar boundary layer, somewhere taken in the critical regime, the subcritical regime. And this is the turbulent boundary layer taken somewhere in the supercritical regime. These are from Venn diagram, the album of two times. So laminar boundary layer, you can see it separates fairly early, almost at the shoulder. The turbulent boundary layer, you will see, energizes the boundary layer, and it could separate much later. So as a result, you get a narrower wave. The base pressure increases, and you get a smaller drag. This would occur at somewhere like 3 to 4 into 10 to the 5th. That is important. The phenomenon is the following. So if I take a smooth sphere and I throw it, if I throw it with a certain speed, this is the air resistance I feel. But if I throw it beyond a certain critical speed, I see smaller air resistance. So if I was playing golf and I hit the ball with all the force that I have, if the boundary layer is laminar, the ball doesn't go too far. But if I'm able to get a boundary layer transition, then it faces less drag and it can go further down. It's very counterintuitive. So if I take a completely smooth ball and I hit it fast enough, then it will go very far. But if I don't hit it too quick, it will go not so far. I mean, much shorter than what I would allocate to. So that's why golf balls are different, so that you can. So if I could make the boundary layer turbulent at this Leonard summit, then I could get the ball with the same force to go much further. So this has been quite well known. So there's a lot of experiments people have done. We did some experiments in the wind tunnel, and so this is oil flow visualization experiment. So this is in the subcritical regime. This is supercritical. So here the boundary layer is turbulent, and here it is a laminar. So there's a laminar separation, and the flow does not reattach. In this case, the boundary layer separates the laminar state, then it becomes turbulent. The separated shear layer reattaches, and then the final separation point is almost at 130 degrees. And you can clearly capture this in an oil flow visualization. The way it is done is, you can take this bluff body, a sphere, and put a film of oil on it, and mix some pigment in the oil. Okay, so this is a white color pigment. Then you run the tunnel. Suppose I want to do a certain speed. So all the oil is pushed back because of the skin friction. But where the flow separates, that's where the skin friction is negative, zero, negative beyond that. So the oil is not able to be pushed further down. So you get the collected oil here. And because of the pigment, you can clearly see the point of laminar separation. It's a sphere, so it's axis symmetry. You do the same thing at high speed. You can see this is all the oil has been pushed down, and along with it the pigment. And then there's another region here. So that's the laminar separation bubble. So there is a laminar separation, there's a turbulent attachment, and here is where this bubble forms, and finally the turbulent separation. So this is very important in sport projectiles. So you take a golf ball, you take a baseball, a cricket ball, more or less this is how it works. So you have to engineer the point of flow separation. Okay, just to show you what it does to the pressure distribution. So there is a pressure coefficient. We are plotting it, let's say, on the circumference. So that's the stagnation point. And if it is a subcritical flow, then you see the black line. So the flow separates somewhere here, around the shoulder, 90 degrees, and then there's a plateau. If you had a delayed separation, then of course you get more suction near the shoulder. Then this is the plateau where the flow is separated, and this plateau is for the laminar separation bound. What happens now is I have a rough sphere instead of a smooth sphere. So as you can guess, the transition is preponed. So this is a smooth sphere. And as I keep increasing roughness, you can see that the separation, the turbulent transition happened earlier. Of course, the minimum drag increases. So if you have a rough sphere, it will have smaller drag prices compared to a smooth sphere. Now, please remember that if you take a cricket ball or a golf ball, it operates around these Reynolds number range, 10 to the 5th. Whereas for a smooth sphere, we saw it is at around between 3 to 4 into 10 to the 5th. So typically these balls are engineered. So some data about balls. So that's the 4-seam cricket ball, the 4-quarter cricket ball, baseball, golf balls. Look at the similarities between the two. Similar diameter, about 70 mm. Exactly the same mass, 150 grams. And very similar Reynolds number. Baseball is pitched underarm. Sorry, without the shoulder rotation. It is overarm. But, actually, some people chuck it underarm also most of the time. So it has a higher speed. Look at the golf ball. Right? Even though it's very tiny, because it's hit with a club, it travels faster. So the Reynolds are a little bit higher. And because of the dimples, you are able to get it more turbulent regime. So the first thing we wanted to do was take all these objects. These are all international quality. So they are either used in Olympics or they are used in Grand Slams, and put them in the same wind tunnel and get data for all of them with exactly the same arrangement. So this required design of the measurement system and so on. We also took these two shuttlebacks, so the nylon and the ductile. And this is the drag coefficient for all these projectiles. Okay. So just to put things in perspective, the smooth sphere is this triangles, hollow triangles. Okay. If you look at a cricket ball, that's this. So an earlier transition. If you look at, for example, a tennis ball, somewhere here. The tennis ball has a much higher drag coefficient, but it is always in a turbulent state, and that's because of these felt. Okay, so the felt already makes the boundary layer turbulent, and it also adds to the drag. So there are many interesting things in this. The golf ball, for example, is here, and these two you would be very interested in: the feather shuttlecock and the magnetic shuttlecock. They have much higher drag coefficient. So if I am a player, then to impart speed to the projectile, so the drag is v square and power would be vq. And you know, shuttlecocks travel at very large speed. And the fastest smash is about 500 kilometers per hour, faster than any of these sports. So the power required here, or the energy spent, is quite high. That's why, you know, these games, they get over very quickly. On the other hand, games like this, cricket, they will go on for some time. Okay, so how do cricketers use aerodynamics? Of course, unknowingly. So if I am a bowler, I want to cheat the batsman, get smarter than me. So I can do that with speed. So if I bowl a very quick delivery, then the batsman doesn't have enough time to react. And before they know the ball, they have to react to it. The other is the lateral movement. So there are many ways you can talk about spin bowling, you can talk about seam bowling, like the cutters. But we'll talk about swing. So the swing bowling is that you hold the ball vertically in a vertical plane, but the seam is pointing towards one of the slips. So if I am a right-handed batsman, then the seam, if it points towards the off stump or to the off slip, that would be one way of bowling. The other is if I point it towards the leg slip. And that creates a lateral force, and the ball can move in air. Spin bowling uses Magnus effect. So if I spin the ball, then there is one advancing side, there is a retreating side, and you will get a pressure difference. So the Magnus force creates the movement. But in the swing bowling, it is actually the boundary layer transition. Okay, so of course the ball is spinning, but the spin is not the one which results in the swing force. I will explain in a minute. So the terminology, let's get used to it. In this case, if for the right-handed batsman, this is pointing towards the off slip. Again, for the right-handed batsman, this is pointing to the leg slip. So the ball would typically move towards the seam direction. Okay. And that's conventional swing. So conventional swing would include both in swing and out swing. So if I'm a batsman, I would like to watch the bowler when they release the ball. And the seam position will tell me how the ball will move. Of course, I need to judge the speed also. If the speed is too low, the ball will not swing. Sometimes the ball will swing in the other direction. So in that sense, if the seam is pointing like this, but the ball moves in the other direction, then I am completely cheated as a batsman. And that would be reverse swing. So here is an example of the same delivery, same seam orientation. It could swing, it could reverse swing. So therefore, there are many questions. A, why does the ball swing? B, why does it reverse swing? You would have heard the commentators say that the ball is becoming old, so it will reverse swing. So can a new ball reverse swing? I see a lot of shakes of it that the ball cannot reverse swing. The new ball. I will show that it can. So the first thing we did was again experiments. So this is a wind tunnel we had. So we took a ball, put it on the sting, no rotation on it. So that's a model simplification. And we can change the seam orientation by taking different models and putting them on the system. We can change the flow speed in the wind tunnel. Okay, we soon realized that the repeatability is a problem because these balls are handmade. So no two balls are identical. Okay, so how do you trust your experiments? So we 3D printed them. This had many advantages. A, we can decide on the design what is the effect of one seam, what is the effect of so many seams. B, we can also now do a Reynolds number matching by taking different diameters. So, for example, this is not a real diameter. It is a larger diameter model, but now I can put equipment inside it, like the pressure scanners. To match the Reynolds number, I can run the tunnel at a smaller speed and load up the effect. We did a lot of pressure tapping on it so that we can do measurements. This can be done on a synthetic ball. You can't do that on a real cricket ball. We also did PIV, for example. This was tricky because this ball is not transparent. So you have to do PIV from the two sides. One shine light from this side and from this side and merge the two pictures. We also did simulations. Okay, because many things were not answered by experiments. So we made these CAD models with mesh around them and so on. So these are the kind of finite element mesh that were generated. I don't think you can see the mesh, but it's a very fine mesh. The seam is completely resolved. So these are largely simulated. Okay, we use a Linux cluster because these are in-house code and they scale up pretty well. Okay, so the first thing is, can we do smooth sphere? Okay. So, you do different Reynolds number. The idea is just to show, these are Q isosurfaces, just to show you that indeed something is happening. This wake is much narrower. So we are able to capture the drag crisis for a smooth sphere. So the boundary layer becoming turbulent. Lambda state, we are able to capture this. Okay, some setup for the experiment. So imagine there's this ball fixed on the sting, and the flow is actually going into the screen. So you can imagine that the ball is coming at us. It's a change of frame of reference. Okay? So you are the batter, the ball is coming at you. So, so if it is coming out of the screen and the seam is, in this direction, and suppose the force acts in this direction, that would be the conventional swing. We call it positive. If the force acts in the blue direction, that is reverse swing. With a brand new cricket ball, we can do experiments at different speeds, different seam locations, and big measurements. There's also lift on the ball that would be very useful for a person like Bumrah, for example. So I don't know how many of you have watched Bumrah's action, very risky action. So he spins the ball quite a bit, okay, and puts in a lot of revolutions. So he's able to generate a reverse Magnus effect. Normally when you put backspin on the ball, it rises. So the faster a bowler will bowl, the more it will rise. But you can get into a very narrow alpha regime, which is the non-dimensional spin rate, where the ball will dip because of the boundary layer transition. I think Bumrah is able to do that. So it's very quick, and contrary to the ball rising, it actually dips and it's swinging, so it's difficult to play, obviously. Okay, so these are the results from the wind tunnel measurements. The top figure is the drag coefficient with Reynolds number. Okay. I will show you what these Reynolds number, how they relate to the speed. Okay. And this is the swing coefficient. This is not so important for us. This picture is more important. So what this is telling us is there are several curves here. So there's a cricket ball, there's a sphere with 5 drip, there's a sphere with 1 drip, there's a sphere with 1 drip and pressure ports. By and large, all of them behave the same way. And depending on the surface roughness and the drip, the phenomena is just preponed or postponed. Okay. So let me just concentrate on the cricket ball, one of the curves. So let's look at the blue curve, for example. What this curve tells me is, if I have a low enough Reynolds number, very low speed, then the seam does not make a difference. The boundary layer is laminar on both the sides, and therefore there is no lateral force on the ball. Beyond a certain Reynolds number, this seam starts to make a difference. It's a brand new ball, where both sides are shiny. But this seam would cause the boundary layer to get a disturbance, whereas this guy is clean, no disturbance. So apparently, the separation here is delayed. What is shown here, the separation here is near the shoulder, as it would be for a laminar boundary. So you get more friction here, and therefore you get a swing. So beyond a certain Reynolds number, the swing coefficient is increasing. Then it saturates. And then, after a certain Reynolds number, something very interesting happens. It reverses. The reason being the following. As I increase the speed, this guy became turbulent because of the seam. Okay. The lower surface, the tiny surface, did not have a seam. But if I go to a large enough speed, it will also eventually become turbulent. Okay. Just at a larger speed, but it will become turbulent. We have now reached a speed where the upper surface is turbulent because of a forcing. The lower boundary layer has become turbulent naturally. This one is not as efficient as a natural transition. Okay, this we have done experiments to show that. Sometimes you can get a laminar separation bubble here, and here you can have a direct transition. So you don't get as much suction in this transition as opposed to this natural transition. So now you have more suction on this side. That is what is shown here. Both boundary layers are turbulent. This one actually separates a little bit later compared to this surface. Therefore, now you get a little bit of a force in the downward direction, and that causes reverse swing. So the brand new cricket ball can reverse swing, but somebody has to deliver it very quick. Okay. As the ball gets older, you can get reverse. So the whole curve, as it gets older, the surface becomes rough, and the whole curve shifts to a lower Reynolds number. And therefore, it's easier to get reverse swing with an old ball, but a new ball, in principle, can also reverse swing. Just to show you, we have done experiments. So this is experiments. And these are CFD. And these are skin friction lines from CFD. And these are flow visualizations from experiment at a particular Reynolds number. And just amazing correlation. So both are kind of showing the same story. Some questions that remain unanswered from experiments, we thought CFD will answer them. Okay, normally it's the other way. You do CFD, some questions are not answered, then you do experiments. Here, experiments were done first. And one question that kept bothering us was, this is the swing coefficient. If indeed the swing is because of the transition of the boundary layer, then why does the swing force rise gradually? What should have happened is there should have been zero swing force, the boundary layer becomes turbulent, and there should have been a step function, there have been just an enormous amount of swing coefficient. So why does it increase gradually? We could not answer this question. Tried a lot. So therefore, CFD was done. And what CFD found is the following. Actually, in this region where the boundary layer, where the swing coefficient is increasing gradually, the boundary layer is not turbulent. It is still laminar, but because of the steam, the transition is delayed. Okay, so it's a disturbed boundary layer, still laminar, but a delayed transition. And then it becomes turbulent, and then of course the coefficient is saturated. And of course later it. So I wanted to give you some idea about the speeds. Okay, so the same figure repeated here. Let me see how much is the time. Almost halfway through. Is that okay, Subhankar? So imagine if I am a bowler, okay, and I deliver a ball, let's say at this speed, corresponding to this Reynolds number. You will appreciate that as the ball is released, as it travels towards the batter, it is going to slow down, right? Because of the air resistance. So the Reynolds number will reduce because the speed is going down. So if I want to track the ball, I should start from this delivery Reynolds number, and this is how it will move towards the lower Reynolds number because the speed is reducing. So maybe a ball is released here, then at the time of delivery it is through a reverse swing, and if it slows down and it reaches the critical speed for swing, maybe it will again start swinging and so on. Or a ball would be delivered here. Okay, so it's a little bit interesting. So I have some examples for you. So let's say there's a bowler at 80 kilometers per hour. You can choose your bowler. My favorite is Ganguly. So we take two situations. Ganguly bowling at Kolkata and at Lords. There was a story, if you remember, no, that he used to bowl better at Lords. I will not say more, but you got the hint. Today we'll give a scientific explanation. Okay? So those stories are not true. I'll tell you the real answer. So Kolkata, the temperature is around 35 on a warm day, not a hot day. Here it is 15 at Lords. So the viscosity of the air, density, so that's the difference. So for 80 kilometers per hour in Kolkata, Ganguly's delivery Reynolds number is 0.8 into 10 to the 5th. Somewhere here. 0.8 into 10 to the 5th. So you get some swing. Same bowling action, same speed, it goes to Lords. It's 1.05. So it's here. So he gets more swing. Okay. So he will be a much better bowler. He has more range. He can swing at will at Lords. Okay. Comes back to Kolkata, not as good. Okay. Let's look somebody like Zahir Khan or Bumrah if you would like. he bowls at 145. So at this temperature, his runners is 1.5 into 10 to the fifth, somewhere here. He's able to get a lot of swing. And as the ball slows down, for the swing coefficient reduces, but keeps swinging. Kumar goes to Lords, he's 1.9. Okay, so he starts reversing. So he can, with his speed, do a reverse swing under cold conditions. Okay, so temperature can make a very big difference. Okay, I'll skip this. These were just some PIP measurements to show you. This is smooth sphere through subcritical and supercritical. The boundary layer is separated much later. And then if you do a sphere with trip again, you get a. So this is conventional swing, you can see. Much more attached flow on the seam side. And then you can get a much more attached flow with the reverse swing at a larger limits on the reverse swing. We also found something very interesting from CFD. So airplanes have wingtip vortices. Okay. So this is how airplanes generate wingtip vortices. This is the plan form. So there is a low pressure on the top, high pressure on the bottom. So that's how you get lift on the wing. But then at the edges, the flow will leak. Okay, so imagine the flow is coming toward the airplane, but it is also leaking sideways. So you get these spiral kind of vortices. These are called wingtip vortices. Same thing should happen in a cricket ball. Okay. So there is a ball, there's a seam, and there's a seam side, there's a non-seam side, and the flow should leak because one has more suction than the other. So you should see wingtip vortices in cricket balls. So there you go. So we were able to see with a cricket ball, you could see wingtip vortices. Just like, so these are the implications. So one is, of course, a ball is coming at you at a very quick speed. And the other is it goes past your ear. And then you have these vortices. Okay, they will have a sound signature. And that will scare the batsman. Okay, so there is I think this is an added component. Okay, so you can have different kinds of wingtip vortices depending on whether the ball is swinging or it is reverse swinging. These are just some more visuals to convince you as to what is happening. So that's the speed of the ball along the length of the pitch. It's 20 meters. So if I bowl at 150 kilometers per hour, I mean not me, somebody, the ball will slow down about 10%. And this is, if you take a top view, this is the bowler side, this is the batter side. This is the trajectory of the ball. So, very interesting. So, if I'm doing a 90 kilometers per hour, okay, that's the kind of swing I could get, almost a meter. So, the lateral movement could almost be a meter. So, there is this misconception that if I bowl very quick, then I'll get more swing. That's not true. You can see a ball like this, 120 kilometers per hour, and you get much smaller swing. The reason is simple. So, even though my force coefficient is saturated beyond a certain Reynolds number, my time of flight is much smaller when I bowl faster. So, the lateral movement of the ball is not going to be as much. So, the bowler has many options. They can either do a lot of lateral movement at a slower speed, or they can bowl quick and cheat the batsman, but the movement will be very small. I think intelligent bowlers use all these options. Here is an example of reverse swing, 150 kilometers per hour. You can see it is reversing. There could also be a situation where it initially reverses and then straightens out. So the curve ball kind of thing. I'm sure you've heard of contrast swing. Pakistanis used to do it a bit. Okay. So, have you heard of contrast swing? Some of you have. So you must have seen the bowlers, they apply some saliva. Now they don't apply. Now they apply sweat. Then they shine the ball. Do you know why they are doing that? That's right. One side, so the team will decide which side will remain shinier and which side will be made rough. So if you are a cheat, which is, so there are many examples of that. Australia. Recently, there was an allegation against a Pakistani bowler that they were using fingernails to roughen the ball. So you can roughen one side of the ball and you can make it the other side shiny. So that's called contrast swing. So we wanted to do experiments. Of course, this is very difficult to do in CFD. You can use some models, but difficult. So we took a ball, used sandpaper, and made one side rough, made measurement. Then turn the ball around, so then the non-seam side becomes rough, which is shiny. Then we roughen the seam, okay, and then again turn it. So it's the same specimen, and we can do these different treatments and then get a fully roughened ball. And we can try to see what happens to the swing and the reverse swing. You'll be surprised. I'll just show you one example. Lots of interesting things. So this red curve is the new ball, which we just saw. Yes, so there is swing and then a reverse swing. Look at this ball, where the non-seam side is rough along with the seam, and this side is shiny. You can get reverse swing at 50 kilometers per hour. Okay. So imagine now a guy like Kumar bowling. So he's spinning, or Ashwin, for example. Ashwin is actually very quick. Maybe even Jadeja is very quick. So these guys are using Magnus effect because of the spin. They can very intelligently use this effect, and they are actually swinging the ball. We have a combination of spin and swing, and a lot of interesting things are possible. What's this? You can see the expressions of the batter. He has no clue what is happening. Okay. So this ball is moving side to side. It's a baseball and a zigzag motion. Okay. The batter has no clue what is going on. It's called a knuckle ball. So there are some bowlers who are branded as knuckleball bowlers in India. Can you name one or two? Kumar started it off. In my opinion, that is not a knuckleball. Okay, a knuckleball should do a side-to-side zigzag motion. I have checked so many trajectories. Nowadays, a lot of data is available. None of them does this, barring one or two. There are one or two exceptions. So we have a hypothesis. Okay. This is what people call a knuckleball in cricket. So you take a ball, hold it with knuckles so that there is no backspin on it, and it turns very little, maybe one or two revolutions throughout its trajectory. So that is marked by this letter A. So the spin is along the horizontal axis. I think this is not going to give a knuckleball. The proposal is to have a ball with spin in the vertical plane. This will lead to a motion of the seam like this, and it will give rise to this zigzag motion, and that would be a true knuckleball. Okay, so we have done experiments, we have done simulations. I will not bore you with them because I want to talk about shuttlecock, which is what the original title was. So sorry, Subankar, I changed it completely. Yeah. So I really love the game of badminton. Okay. And You know who this is? This is my favorite player. He doesn't play anymore. Linda. Yes. This is my favorite picture of Linda. Okay, so there are two of these shuttles, the duck feather and synthetic, and the idea is to figure out why are they different aerodynamically. Okay, I hope you are able to see the challenge. Duck feathers is cruelty to animals. Okay, you are peeling off feathers and to play. Okay. Of course, one can make a case that these are already dead animals, but that is not true. I mean, people breed animals and use their feathers. So, and plus they are very expensive. And thank God they are expensive. Okay, if they were cheap, you would see more animals being killed. So I'm actually happy that they are expensive. So now you have a challenge to make a synthetic shuttlecock. Do you know what is the weight of a duck feather shuttlecock? How many grams? Take a guess. Any badminton players here? How many? 20. 20, okay, that is one guess. 21. 22, yeah? And anybody else? Ah, you are actually right. So actually a duck feather shuttle is only 5 grams. Only 5 grams. Okay? And that's because these feathers are bones. So they're extremely light. This is called the hollow bones, extremely stiff. If you want to make a synthetic shuttlecock, you have to have this cork. Then you have only about 4 grams of nylon. And you must distribute it. The center of gravity should be maintained. The size should be maintained. You can't say, this is a small shuttlecock. That doesn't work. So it has to be the same size, same center of gravity. So it's actually an engineering challenge. Within 5 grams, produce this. And that's why those of you who play badminton, there are so many designs in the market. There is 350, 2000, 90, blah, blah, blah. Okay, so very little is known about shuttlecocks. So Cook actually did the first set of experiments, and what she said is that the entrainment is very important. So the flow goes in through these gaps, and it creates these annular zones. And there's a jet-like flow here, and that actually is very important flow structure. Again, we went to the wind tunnel. Yeah. And you can leave all the curves except the ones I tell you. So 2 curves. So one is this solid line. That's a duck feather shuttlecock. Okay. So this is Reynolds number, speed, and this is the drag coefficient. So this doesn't change much. Changes, reduces a little bit, doesn't change much. Look at the nylon shuttlecock. Okay, very high drag coefficient at low speeds, and then it starts reducing, and by the time you hit a smash, 60 meters per second, it's become almost like a square cross section. This is a splendid case for fluid structure interaction. Okay, because you have a high speed projectile, very thin membrane, it's deforming, changing the flow. Okay, so we'll see what we learn from this. So very smart students, they made these models, CAD models. These two are AS 350, this is Aerosensor 2000. And I said, why don't you make one model where you close all these gaps? Okay, so the skirt has no gap, but it is hollow inside. So there is still there's a gap. Which one do you think will have the least drag? And which one will have the highest drag? From your knowledge of flows. I had guessed it wrong, so don't be shy. Okay, so it looks like you don't want to say it loudly, but you have made up your mind. That's fine. Say that again, please. Feather one? Feather one will have least drag. Okay. Okay. Actually, this one has the least drag. And it was so counterintuitive. I thought this is a bluff body and it should have the highest drag. Okay, and that's the beauty of a shuttlecock. The gaps actually are very important. They are the ones which lead to drag. Okay. So we made these grids. Okay. Some convergence studies, sorry for the fonts and stuff. Reasonable convergence, okay. Okay, so this is the drag coefficient. So this is the synthetic shuttlecock. In fact, you should have guessed this. I showed the wind tunnel result, right? At low speeds, a synthetic shuttle has the largest drag. And that is by design. Because with speed, it will get squeezed and its drag will reduce. If you already make a shuttlecock which has small drag coefficient at low speed, by the time you hit a smash, it's nowhere. Okay? So therefore, you design something which has a high drag to begin with, and then slowly, the drag will reduce and it's kind of. So it has the highest drag coefficient. This is feather, and this is the gapless. Did with some detour this one. Okay, this is the flow. So this is your synthetic shuttlecock. This is the duck feather, and this is the skirtless. Sorry, the gapless. The skirt. You can see thing which determines the drag is the momentum deficit. Okay. So even though this has a very large recirculation zone, the momentum deficit is much smaller. You can see it is very large here, small here, and very small here. So how much momentum am I using in a given control volume? Okay, so we were interested in finding out which region of the shuttlecock produces the drag. Okay, is it the skirt? Is it the cork? Is it the middle skirt, outer skirt? So these are the regions 1 to 6. Okay, so 5 and 4 are the outer skirt. 4 and 5. So one thing is viscous effect is very little as expected. It's mostly pressure driven. And most of the drag, okay, almost 75% is generated by these two regions. The outer skirt, the medium skirt and the outer skirt. Okay. So that makes sense. Okay. I'll show you why. So we plotted the pressure distribution, and what I'll do is I'll take a line here along the spike of the shuttle and show you the pressure on the inside and outside. The drag is created by a component of the pressure difference between the inside and outside. If the two pressures are same, there will be no drag. Okay, it will just cancel out. So I'm sorry you can't see the color very well, but you can see that there is a fairly large difference here, but very little difference between the inner and the outer. So in the next figure, I will take the pressure difference and plot that. Instead of two curves, there will be only one curve. It's easier to see. This one. So along the length, this is the pressure difference on the stalk for the gapless. This blue line is for the feather, duck feather, and this is synthetic. Of course, we know what is the effect of drag on this, but more importantly, the playing quality. If you look at the center of pressure distribution, this is very feather heavy. So the pressure distribution, the pressure difference is more towards the feathers, away from the center of gravity of the shuttlecock. Whereas in a synthetic shuttlecock, it is quite evenly distributed. So if there is a small damage or change to a shuttlecock, the feather shuttlecock is more difficult to control. It has a bigger moment because the whole pressure distribution is outside. So it requires a more skillful player as compared to a duck feather shuttlecock. So the first thing, if you want to design a new shuttlecock which resembles, is bring bring this guy, distributed guy, more like the blue guy. Okay, that's a clue. Okay, then we went, so these were all with a rigid shuttlecock. Then we tried to do a fluid structure interaction. I'll be done in 3 minutes, Subhankar. Sorry, just delayed by a few minutes. So this is the pressure distribution on a rigid shuttlecock. This is when it deforms, you can see. So this is coming from fluid structure interaction, a spontaneous shape like this. So how are these calculations done? So you make a fluid mesh, as shown here, and then you make a structure mesh. Okay, so we have a structural solver, a fluid solver, we couple them through scripts. So I'm seeing the shuttlecock from the top. Okay, so I'm seeing it from the inside. So it's as if the shuttlecock is facing me, the cork is towards you. So this is the skirt. So at 30 meters per second, it remains almost axisymmetric. Then it starts buckling. So at 40 meters per second, you get a squarish cross section. And then at higher speeds, you start getting vibration. So actually these feathers, these skirts, they start vibrating, transverse vibration. And then at higher speeds, in addition to these transverse vibrations, they start moving circumferentially. It's like a stall. Okay, so therefore the images look very blurry if you do them in a wind tunnel. So in fact, this is some stills that how you can see from this image, for example, how this cross section seems to be kind of spinning because the deformation is moving circumferentially. So overall, if we compare now the wind tunnel measurements with the fluid structure interactions, so that's from the wind tunnel. Okay, CD versus speed, and these are 3 different models based on the elastic modulus of the shuttlecock and so on. So you see, this one is quite capture all the details. So there is first some kind of axisymmetric deformation, then actually it buckles. And we see this feature in the wind tunnel experiments also, which we missed earlier. After the numerics, we saw that yes, there's a change of slope. So this is an instability, buckling. And then, of course, we are not able to do calculations beyond this because the mesh becomes incomplete. Okay, I will stop here. I will just leave you with a picture of the frisbee. So we are doing some calculation on frisbee, how the boundary layer transition on the frisbee and the flow in the cavity. So I just stop here. If you have any questions or comments, I'm happy to address them. Thank you.
Very much. From the audience, this is actually, I think, in our whole country, Sunetra only presented some of this kind of topics. There is a high possibility, okay? So, we have come here with very good experience, very good exposure by science. So, if you have any question, anything you can ask.
Sir, do we have effect of humidity on cricket ball?
Absolutely. So there is there's a definite effect and there is a speculative effect. So humidity means there will be more water content, moisture, right, in the air. Do you know what it does to the density? If I have a more humid air, does the density increase or decrease? It will. I am asking this because I know you will give the wrong answer. Actually, it will decrease. Oxygen, what is the molecular weight of air? Okay, and what is the molecular weight of H2O? Okay, so actually, humid air is lighter because it's not water; it is water vapor. So you have to always think in terms of 22.4 liters in 1 mole. So effectively, what is happening if I have more humid conditions, I have lower density. So for the same ball speed, I have lower Reynolds number. Okay, so now it depends on the bowler. if a guy, he was a very fast bowler, and he was, he had a runner somewhere where the flight time of the ball was small, so the ball was not swinging much. Now the effective, so it's the same speed, but the ball will swing more. So the batter sees the same reaction time, which is very small, but the ball is swinging a lot. It appears the bowler is more lethal. Okay, so that is a tangible effect. Some people argue that humidity also changes the seam. So there is some cock and bull story that the seam will absorb water, so it will become thicker, and therefore it will swing more. I am not very convinced that a leather ball can absorb water from atmosphere, but I have no evidence otherwise.
Swing the ball with an upright seam, like Mohammed Sami. What is the reason behind that?
So upright seam, there are two possibilities. Okay. One is the guy is not swinging the ball, it is a cutter, it is seaming. So it hits the pitch, and because of the dynamic action, it's a collision, right? And it's a spinning ball. So there's a small angle and it goes either way, and there's a lateral movement. That is one. But I think a bigger possibility is that balls are not spheres. Each ball has a bias. We saw this in our experiments. So even if you keep a ball at zero seam orientation, it will have a swing because it's not a sphere. Okay. So if you are a smart bowler, you can use that to fool the batsman. The batsman will think it's coming upright, but it will swing. In fact, you will see sometimes bowler will, while bowling, they will take a look at the ball, they will throw it. Much like the tennis players. So you have seen when the tennis players, they are choosing a ball. So, you must have seen like Alcaraz will choose 2 balls out of 5 balls. So did you see the recent French Open? Tennis? Okay. So this is a clay court event. So people like Alcaraz, they will ask for 5, 6 balls. And they keep 2, one in their pocket for the second serve, and one, of course, for the first serve. So he chooses from 5 or 6 balls. So he's just throwing them, bouncing them, and the ball boys and boy girls are just around him, waiting for him to return the ball. Then he will. So it looks very amusing. How do they choose these balls? Okay. So these players, they have a field. They are able to see. So, for example, in tennis, the guy would like a ball which is heavier. It has more fluff because it will spin. His serve has a lot of spin. But there could be a person who just serves very quick. They don't want the ball to spin. They just want it to go quick. So they will choose the ball in some other way. So to answer your question, yes, it is possible to swing with an upright seam. But I think it is because of a defective ball. But all balls are defective by definition. They have some bias. I hope I have confused you enough. Chandan, please.
I was actually about to ask you that, do you think by doing a dynamic simulation of rotating balls can give us more insights?
I think they should be done, and 2 of my students are doing that, and we are able to find Magnus effect and reverse Magnus effect. But these are very difficult simulations, and the interpretation is even more difficult.
So I was just curious that some of these conclusions, can they change?
I think they can. Some of them can change. So my estimate is that they can change by about 30%. So if you look at if you look at a ball with a backspin versus a ball without a backspin, the change in force coefficients could be as much as 30%. So qualitatively, things will not change much. But yes, quantitatively, they could. You're absolutely right.
I have a second question about the shuttlecock. So as you have shown clearly that without the hole, the drag coefficients are very different, and I think the porosity has a big role to play there. So while we are designing the synthetic cork, so basically, if we keep the porosity constant and then change the design, like or change the last, like you have different phases, and if we play around the porosities of all those things for the first and last portions, but keep the actual overall porosity same. How do you think things will change? I mean, have you thought about it, or why this particular design is opted? So that was my curiosity.
Right. No, that's a $1 million question, and I think it is truly $1 million question.
I was thinking who designed this, of course, might have some engineering consideration.
So if you look at Yonex, okay, even on their website, they give out some information. So they will say, I think the hallmark of a good shuttle is its trajectory when you do a third court to third court throw. Okay, so a good shuttlecock should go up and it should come down vertically. Okay, just drop, because that's what a feather shuttlecock does. And they very proudly show that this shuttlecock does that, this one doesn't. I think they do all these simulations.
So I think the answer lies in the center of gravity.
Okay, so to add to that, let me point out, you may already know this, but let me point out another very interesting aspect of a shuttlecock. I hit a shuttlecock. I hit cork first, right? Does it reach you cork first? So I hit cork. So the cork is facing me, and the feathers are facing you. But when it reaches you, it has flipped, right? So actually, it's an unstable configuration. So a shuttlecock is designed that as soon as I hit it, it flips. So the center of pressure and center of gravity have to be in such a way that they flip. Imagine I hit a shuttlecock and it reaches you feather first. It would look very odd, right? Then the game is over. So that also has to be kept in mind. It's a very interesting sport. Hats off to these people who designed them. It is really an engineering marvel.
When they are in air, it's actually an FSI case because they have 6 degrees of freedom. So that can do anything.
Can do anything.
With also unsteady air around. So it's a very complicated process.
It is a complicated problem. There's Subhankar, one question here, if you allow me.
I have one question. But, sir, I have a question regarding the shuttlecock. Like 5 to 10 years back, synthetic shuttlecock used to like once I hit the cork, it don't reciprocate, means it requires more force, but it doesn't reach to my opponent who is standing there. So generally we used to apply a simple logic. We just used to put paper or cardboard just above the cork place, and after that less force was required, and it gets easily, just like you have said now, immediately it shows that it is going up and it is getting instant after placing the paper or the cardboard inside. But nowadays it does not require such things. So, sir, what was the main or key reason behind this?
Yeah, so the material distribution. So you have only 4 grams of nylon. Okay, so the quality of nylon has improved, quality of processes has improved. Okay? If you notice, they are able to make shuttlecocks for high temperature, for low temperature. So winter there will be a different shuttlecock. So you know there are green, blue, and red indicators. So they have really perfected it. So I think it is just better understanding, better materials, better workmanship. You are right. About 5 years, not 5, maybe about 10 years ago, people used to laugh at synthetic shuttlecocks that they are not used. Now BWF will most likely use synthetic shuttlecocks in their tournaments at competitive levels. My guess is 5 years, synthetic duck feather shuttlecocks will be gone. They'll be banned. You can't use them. That's my guess. So it's just technology.
Having any relation with the track.
I'm sure it has. I mean, it just they understand it. With my limited understanding, I don't know the reason. But see, at Yonex, I'm sure there are hundreds of engineers doing this. They are good. Leaning, they must be doing this. They know all this.
So if there is no more question, we can go to the next one. Actually, we shall take a tea break. Okay. Tea break maybe for 5 minutes, not for long time. Then Professor Chandan will start. So, just all these password questions. Otherwise, I should not do it.
Yes, sir.
हमारा पासपोर्ट बन गया पासपोर्ट
cricket, while hitting the ball, we used to choose a ball which has a thicker seam. Thus, it can swing more in the initial stages. Sir, I'm thinking that actually I'm a spinner. My coach is always telling me to spin it with an seam towards since I'm a left-arm spinner towards the leg slip of the batsman. But does Magnus effect has any relation with the seam?
Very good question. Very good question. I think it has. So we have looked at. So we are looking at now the effect of swing on the Magnus effect, and it is significant. Try to reinterpret your question. You are always spinning. So the axis of spin is always normal to the plane of seam. So
Yes,
the
sir.
seam is not wobbling.
Yes, sir.
If it wobbles, then of course it's a completely different thing. You are asking that if I have seam versus I have no seam.
Yes, sir.
Will there be a difference in the
saying
Magnus?
that if I have I'm spinning it with an upright seam, and again I am spinning it with a say orientation towards the first slip. Does
Yes,
it-
of course. You have a direct effect because then your axis of rotation is different. Okay, so I put your question now into. There are two parts of the question.
Yes.
One is the axis of spin important?
Yes, sir.
That's your first question.
Yes.
The answer is definitely. Because Magnus force will act in a manner that there has to be advancing side, there has to be retreating
Yes.
side. So if your seam is upright,
Yes.
then whatever spin you give is directly contributing to advancing and retreating side.
Yes, sir.
difference.
That ugly and
Right. But if you tilt it,
yes, sir.
then only a part of it will.
Yes.
So it will not be very effective. I think the other one should be more effective, the upright seam. But you will also get a swing.
Yes, sir. That part will be there, sir, as that is an old ball.
Swing will also. Interesting. You should collaborate. So you also do fast bowling or only spin?
Yes, sir, I'm a spinner.
Okay. So yeah, we should talk here. I think we need to make measurements. So I'm trying to get some sensors. You want to make some measurements. So where are you?
Sir, I'm a PhD scholar.
Here.